Hello again. Today I'm going to talk about noise, height fields, and voxels. I guess it's called voxel maps. I'm not totally sure what it is. It's a height map made of voxels. I don't know. So let's start with just running around here. So on my channel you have the one like Minecraft world video where I did some cubes. Kind of looked like small Minecraft map, really tiny, like 8 times 8 times 8 voxels or something like that. This is bigger. This is much bigger. And the code is in the description for those that want to just turn off the video and jump over and take a look. And for the others, let's talk about, I forgot to add in fog here. Should we do that? There we go. Should we talk about how to create a voxel map like I'm running around on right now? Okay, so let's open up some code, quit out of the program, make some space, then draw, and then we need a drawing tool. Anyhow, height map, let's start with that one. So if we are looking, let's see, so I draw this correctly. If we are looking into a scene, so everything gets smaller farther away we are, so that's the Z. Wonderful height map. Height map normally is an image, and you color in the image with like blue here maybe, blue there, blue there. That basically means that on these positions we just going to have the same height. But height map is really just an image. So you take a drawing tool of some sort and you draw in. You draw your image in any tool, and then you put it into a 3D program, someone else's or yours, and the 3D program reads the image and says like, what's the values on the different X and C on X and Y on the image? Oh, it's value 2. Let's draw the height 2. So each of these, let's say that they have height 2. All of them, except over here. Over here, the person was drawing something else on these guys. So then we should actually have representation in the 3D that represents that. This is a higher up. So you have to pretend that you don't see the red things that draw below it. Let's draw this with another color. So the height is determined with the value you have in your texture. Well, so either you can draw it or you can just calculate it with some algorithmic function. You don't need to have a drawing tool and like drawing the height map. You can use something else, and Perlin Noise is something that's often used. I do have Perlin Noise. I have tried it. I could probably show it. I don't have an image of it right now. So what we do is actually look at just an image on Google instead. And there we go. We have Perlin Noise. I will say all of these 3 are Perlin Noises. Perlin Noise is a smooth changing random value. So the random value would be random, but the Perlin Noise changes smoothly. And that makes so you can make hills of it, and you can make one of these height maps. So yeah, that's the Perlin Noise. let's jump into, let's delete this first. There we go. Let's jump into, should I jump into explanation of Perlin Noise? Yeah, right. So you need a random value for, or height value for x and y in your height map. But since you're not drawing it, you're going to ask the algorithm, and you're going to ask it, hey, I have a position here, I'm there. Can I get a height value for this position? And the Perlin Noise randomizes a vector and put the vector on each corner of this square, or you can make it in 3D, would then be a cube. So it draws a vector and draws one, it calculates a vector for each of these corners. After that, it calculates this vector from the closest point where you are. So this would be integer, so say it's 52, but you are currently at 52.3. So it calculates that vector. After it calculated that vector, let's see if I have another color. Do I have more colors here? I do not. After it calculated that vector, it makes a dot product of those two vectors. It takes those two vectors, fold them together to a scalar number. And that's our random number we almost going to use. That is done for each of these. Let's see, where should that be? If I have, is that there? Was such a long time ago since I had a math class, so I'm sorry if I'm totally wrong with the result, but it's kind of it's not the math class here, so well, it's a computer class kind of thing going on. So if I'm a little bit wrong on it, like, forgive me about that. Anyhow, it calculates these 4 scalars, that's a dot product of this random vector that is in each corner of this triangle where we're trying to calculate our height map. And we need to do that for each point in our height map. So it becomes quite a lot of times we need to run through the Perlin Noise, because it needs to be done for each point. Anyhow, we aren't done. We have the dot product, but we have 1, 2, 3, 4 dot products, and we go into now I'm losing the word here. Is it called integrate? Interpolate? Integrate? What is it called? God, I forgot. How can I forget something like that? It's called interpolate. There we go. We're going to interpolate between them. So we're going to pick 2 of them. Let's pick these 2. Those 2. And we're going to use, I think it's the size of our vector here, and pick where we are here. So we're going to have that value, and that value is going to be interpolated between those. We're going to pick a middle ground. We're going to do the same with these 2, and we're going to pick a middle ground of those 2. So now we have 2 new values, 2 interpolated values of the dot product of 2 random vectors on each corner. So 4 vectors on the 4 corners that we have 2 interpolations of. We got 2 values from that interpolation, and then we're going to take those values that we just figured out from this interpolation, take those 2 values and take an interpolation of where we are on with this vector on that value, and that value that comes out there, That's the value we're going to put into our height map. And that's used to calculate the height. And we need to run this for each vertex in this height map to make our world very confusing. So let's clear this out and go into code. And we get into to interesting code later. That's not the Perlin. I'm going to get to that. So here we go. The Perlin. Perlin was a dude in 1980 something that created this algorithm because he wanted something looking natural in random. And after that he made something called simplex Perlin that was patented, that people didn't want to use for obvious reasons, and that was faster than Perlin, but Perlin, obviously, after you heard my explanation, is kind of slow. But after that it comes Open Simplex, which is a free version of it. This is Perlin though. So first we're going to send in where we are. We need that square first. So we are here, but we need the corners. So this is just going to calculate the corners, going to floor down this value and floor down oops, sorry, not that one, floor down the other value also. And then we're going to calculate the other side of this square so that we can represent the square. We're going to determine interpolation weights, that's our vector here. And that's this part. We need to interpolate grid points. So we're going to use the dot grid gradient, 2 of them, and that's the vector here and over here and over there, but in this case it's just on the left side. I draw all of them here. So we need these vectors, we need the dot product. Let's draw it like this time. Wherever it becomes, we need that. And we're doing, after that we come down to interpolation. We're going to take these values, going to interpolate them, saying that I'm here, I'm going to have that value there. I'm going to do it once more over here. There we go, interpolate that. And then we're going to interpolate those values that we got. We take those values, 2 values. I say I want the value there. So that's what we are doing. And this is in 2D. I mean, there's a lot of stuff going on. So think about this of doing it with Voxel. It's going to be 3D, right? So I had actually serious problem. This code is from Wikipedia. So if you want to see this code, go to Wikipedia and you find it there. And yeah, I've scrolled up here just to illustrate how much this will be. So all of this, doing the dot grid gradient, doing the dot product is kind of cheap, but this one, random gradient, we need the vector. It's some pseudo random thing here. That's like, yeah, that's I guess correct. I hope. I don't know. I have seen pseudo-random before, and this looks like pseudo-random to me, so that's pseudo-random thing is correct. Or well, it looks correct. I don't know if it is correct, but it looks correct to me. But it's a lot to do, right? For each point. And yeah, I found this online when I'm not totally sure of what his license for this one was. I just pasted in where I snapped this from. But the point here is that to make a 3D, we don't just need the 2 sides interpolate. We need the other sides pair face of the cube also. So that's exactly what this code does. You can see it has Perlin, has X and Y and X and Z and Y and Z and Y and X and Z and X and Z and Y. So it really takes all edges around, not all of them, just 6 of them. Anyhow, for every face, 6 faces on a cube, it do a Perlin. And then it can do it multiple times, but that's another story. That's where you're layering waves on top of each other. If you just have one wave, you can kind of see it as this is a wave, but if you layer waves on top of each other, then it's really hard to see that after a while. So that's why I have the 4 around here. We can ignore that for now. So the Perlin Noise. So my interpretation of it, because it's actually just plussing it together here, I think that's wrong. Anyhow, my take on it, how I would do it, is kind of the same thing, but instead of just plussing it all together and looping around here, I interpolate between one Perlin with the next one, with the next one, with the next one, and the next one, and just return that. But it still calls like 1, 2, 3, 4, 5, 6 times. It calls all of this crap 6 times. So what have we learned? We have learned that this probably takes a lot of CPU, and I tested it. It do take a lot of CPU. What can we do? Well, we learned how Perlin works, kind of, at least. If you have like kept up so far with this, like, congratulations to yourself. Either you read on Perlin Noise before and know much more than I do, then question why are you looking at this, or congratulations on you, otherwise you would have clicked off this video for a long time ago. But now we know kind of the basis behind Perlin, and it's kind of like you pick a location and you calculate the random value in the corners, and it's really important that you can move this X here to the next square over when you're moving along in your world, and these two remains the same. Those values has to remain the same, and I get new values to interpolate against. So we need an algorithm that's keeping those values the same all the time. We need them to have a value that we can interpolate between in some way, and it would be super nice if we could do this as a cube without doing too much calculations and still have it looking fine. Even if it's not like as nice as Perlin, just yeah, it's looking fine. And now comes the question, can we do that? And of course we can. That's why we are here, right? So we take our value here, we calculate the floor of it, so we discard a dot something in the numbers, and we calculate that point, and we calculate that point, and then we have all the other points, so we know all the other points, so we know our cube. And when we have all the corners of our cube, we could make one of those pseudo-random things that I said, like, I recognize as a pseudo-random thing. Let's create one of those for each of these points. So this is not a vector this time, this is just a scalar, so it's just a number. This is just a number, but it's easier to draw like this. So we get a number for each corner. There we go. And let's start with that and take away that and go and see here what we're doing for magic with those numbers. Just make a cosine of it. Instead of all of this interpolation and all of that, just make a cosine of it. And we are done. Also, I see that this implementation only has 2D. I have a 3D version here. Let's go into the 3D version. Because that I've been talking about, it takes a lot of processing. I should actually show the correct version of it. So here we have the 3D version. So of those values in the corners, just make a cosine of it and you get from -1 to 1. So we have a known value from 1 to 1. What can we do more? We can say that when we are moving away from a corner, so when we are over here, then we are kind of close to this one, kind of far away from that one. If we would move even closer, then we would be extremely close to this one, very far from the other. And we can use a little bit of multiplication to add as a factor to this one to tell how important it is. So when we are close to something, we will more or less get only that value. When we are in the middle, we get an interpolation between these two. And the interpolation, we're just going to plus it together. And I said on the other one, I didn't really believe that we plussed it together and that was correct. But in this case, it is correct. Because it happens to, let's put in the comments again, because they went away. Because it happens to equal out when we are very close to one point, we get much of that point's value, very little of the other one. So we can just plus them together and we get the value, which I bloody hope is correct, because this be me thinking it out, is between 0 and 1. And this code is, by the way, is for a cube, so it's the 3D version of it. Let's remove that. And that's a page of code, and up here we had this called 6 times. That's this page, that's called this one, and that one doesn't take a page. There's a lot less code. And you already seen the result of this. The result is the height field. Let's see that. And actually, I'm not even using 3D here. I'm just using 2D. Voxels would be using 3D. I'm just using 2D. Voxel doesn't really have a height field. They have multiple height field, you can say. So we're calculating our height field. That's we're doing here. Sorry for the messy code. It's my test code. So we take the player's position. We plus on an X for where we are in the screen. So the screen again looks like that, and currently we are drawing this. But we are really, location is over here. That's where the player are. But we're drawing this one over there. So that value, we need a value there. So that's what we're doing here. We have a position plus X. X just happens to be the number of blocks we're going to draw out here. So I'm going to iterate from block size minus block size times 2 to block size times 2. I think that's 64, so 128. I'm going over 128. And I'm doing that in the other direction also, 128. And then I get a Z value, because the noise returns a value from 0 to 1. And I just multiply that with the block size, which is the height in this case also. So we have, I think it's 64 possible Z in heights. Now I'm confused with you, because I said Z was this direction before, but I calculated it as that here. Anyhow, that's what we're doing here. And then we're checking if the Z happens to be underneath the water level. If that happens, I just set Z to the water level. And then you've got some messy OpenGL code that half shouldn't be there, because this load identity should really be outside here, and you can reduce complexity of this, and these rotations could probably be grouped together somehow, and all of that. We're going to translate a bit, and we're going to draw a cube. So we are at the space on the screen. Then we're going to see, are we below or at water level? In that case, we're going to draw water. This cube 3 is water. Else, if we have grass enabled, I didn't show that, then we're going to draw grass, else we're going to draw something else. And then we have an error in my algorithm, because I mixed together voxels and height maps, and voxels shouldn't be used with height maps. Height maps should be used with height maps. So you should only draw a plane that consists, of course, of multiple polygons, squares in this case. Polygon normally not a square, so you probably have to draw them like this. That's what a height map should be used for. Not some idiot like me, like, oh, I'm going to draw a cube here instead because I'm special. But that's exactly what you're going to do. You're going to draw a lot of cubes, and the height of that is determined by this noise function. So if we are at water level, we're going to draw all of cubes at water level, else we're going to draw them higher up, and this could mean that we get a cube. Let's draw a cube here. A cube that cube represents this square here, but it happens to be empty here. There is nothing here. And then we're going to draw a next cube here, but that one wants to be lower down. It wants to be hiding in the floor. And that means that we get an empty space here. This yellow space here becomes a hole in our texture. If we had used the correct height map, this wouldn't happen, because then this vertex there would be one down, that one would be one up, this would be tied to that one. We would get the slope here instead. Very messy. We would get the slope up there. We're not getting that this time. So we're drawing 128 times 128 of them, or let's see, it could be that I have okay, I'll go 32. We could draw 62 times 64 times 64. So we're drawing that, and in the end here we're doing exactly the same. We're going over everything again. If grass is enabled, taking out the exactly same noise value, doing the exactly same transformation, and if we are above water level, we take another noise value, and this time we're going to just, we could see the noise values that become different each time we run it. Or in this case, I want another noise value, but I don't want to reseed it. Have the seed, let's see here. That's how I do my random values. So this pseudo random, I have that. I can update that and get different maps all the time. But it's a much simpler way to get different maps. These maps are big, right? They're seriously big. So we can just offset our X and Y position some, and we get another value. And who's going to know that the flowers and shit comes from a location 1,000 away from that way? I mean, no one knows, so just pick your value and there you have your seed. And then we draw a little bit of grass. So let's run that again. Let's jump up here so we can look around. Is this a good spot to look around? Maybe. Here's a good spot to look around because I can see there is something over there. Now we're going to turn off the fog. So here we got everything rendered. And if we are going to be even turn off the grass and get some winter going, So this is what our height map with voxels had created for us. So we have this plane that's the 64 times 64 voxels. We have the water. At the water level, all the cubes that represent water. And we have the height map, that's the noise function that sets the height of each position here. And I can just walk over here and it's just updating. And for every frame, it recalculates everything. And that's not needed. I could just recalculate what pops in and what goes away here. I'm actually recalculating what's behind me also all the time. Totally unnecessary. I'm almost drawing it also. See, this is very unoptimized code. Very unoptimized code. But I've moved forward. I could just recalculate that was popping in. But like I said, I recalculate everything all the time, even when I'm spinning around here. So it goes quite fast to recalculate everything. Sorry for making someone sick there. So that's why I decided to go with this lesser noise algorithm than the Perlin, my own algorithm, because it's super fast and I can recalculate everything. The things that drags down my implementation here is the voxels. I mean, have you seen my OpenGL 1.1 implementation of voxels? Oh god. I mean, you can make lists and you can make vertex objects and you can push down the data to the graphic card. You can have a shader making them. You can make them in so many ways that's so much faster than this, but this is pretty fast too. Anyhow, in this program, let's talk about the program a bit then, if someone wants to download it. Of course, you can look up and down, left and right. When you look over to a side, you actually walk that side when you press the keys, so you can walk around with the keys like normal. I couldn't hide a mouse pointer because I couldn't figure out how, which means that you can only look behind you, but then your mouse pointer is on the right side of the window, so you need to go around again and look at the other direction, kind of. So you can't go more left than that. But with G here, you can turn on and off grass, and when you turn on and off grass, everything becomes green, and you also get this grass. Let's walk over here. It's easier to see. So you get this grass rendered, a little bit wrong color I have to say, because it's really hard to see when you're just looking down at the floor here. But over here we can see the grass, and you see some flowers also. Then you can enable fog, and that is made so it hides what kind of okay, I can only work this way. So it hides what's popping in. So if I remove the fog, you see that objects are popping in here into screen, and that doesn't look very nice. We put on a fog and we can't see that. And of course the fog should be further away, but to have it further away I have to figure out a smarter way to drawing this. So it goes a little bit faster, because voxels apparently take a lot of CPU. Yeah, so voxels takes a lot of CPU, and let's hide that fact with this fog. And when I turn this grass here, I could, was it nighttime? There we go, daytime. I could make a winter themed map. Everything is frozen, or with grass, call it daytime maybe this time. I like that better. So that's the program, and turn it off. Let's see if it's anything else that's interesting to mention. Everything else here we have gone through in other videos. If someone say like, oh, that's cool, I need to download that, but I don't understand the rest we have in other videos. What we have a new function here is a glute passive motion function. Passive motion takes in an X and Y, and that's as fast as your mouse cursor is in the window, you get this. And I use that for my rotation, for looking left and right. And I decide where to walk in the keyboard function when I press a key. Depending on, first I just assign everything. I'm walking left and right and up and down and all that, and fog ignite the grass, I can toggle those. And then depending on my rotation, I decide what position to update how. I think that's it. The code you can download in the description, and if anyone do anything nice with this, please let me know. And one nice thing would be to replace this with something that's faster to render, because that's probably what I should do next, right? But we will see, we will see. A lot of talking this video, a little bit less of actually showing code. But it is what it is, and I hope it brought something to some of you. Happy coding!